In this session, we will understand sets, subsets, and their further properties with examples. First, we will discuss about sets. A set is a collection of well-defined distinct objects, and this collection is enclosed by curly brackets. Sets are usually denoted by capital letters A, B, C, X, Y, Z, etc. And their elements are represented by small alphabets A, small b, small c, etc. If A, small a, is an element of capital A, set A, then we say that A belongs to A, and mathematically we can express in this way. Similarly, if B is not an element of A, then we write this expression mathematically this way, and we read it B does not belongs to A. Representation of sets. There are two methods of representing sets. First is roster or tabular form, and second is set builder form. In roster form, all the elements of a set are listed. The elements are being separated by commas, and that list is enclosed within curly brackets. For example, if you have to express set of all squares, square roots of 9, then it is expressed as A is equal to 3 comma minus 3. Just we list square roots of 9 and we enclose that list with curly brackets. But in set builder form, all the elements of a set possess a single common property, and this same set we can express this way. The set of all square roots of 9, in a set builder form we can write A is equal to x such that x square is equal to 9. Sometimes we can use, instead of columns, we can use vertical line to separate element and its property. There are some standard mathematical sets. First is set of natural numbers. It is denoted by script n, and elements are 1, 2, 3 up to infinite. Second one is set of whole numbers. It is denoted by script w, and it is set of natural numbers with 0. Then third one is set of integers. It contains natural numbers, 0, and negative of natural numbers. It is usually denoted by script z or sometimes script I, and this is that set. Another standard mathematical set is set of positive integers. It is denoted by z plus or sometimes I plus, and it is nothing but set of natural numbers. Similarly, we can define set of negative integers. It is denoted by z minus or I minus, and it is just minus 1, minus 2, minus 3, or we can denote it by minus n. Next set of rational numbers, it is defined is denoted as script q, and it belongs to element of type p upon q, such that p and q belongs to z, with q is non-zero. And to avoid repetitions, we can take GCD of p comma q is equal to 1. For example, this 5 upon 1, 3 by 2, or minus 2 upon 31, 25 upon 101. This all are belongs to rationals, and it is infinite set. Then it's another set is set of irrational numbers. So the numbers which are not rationals, we can say they are irrationals. For example, root 2, root 5, or a very well known number pi, or Euler number e. These all are irrational numbers, and q dash is the notation we can denote set of irrational numbers. Next set is set of real numbers. It's all rationals and irrationals combinedly. We can say it is set of real numbers, and it is denoted by capital R, or you can say script R. Then next bigger set from real numbers is set of complex number. It contains real numbers as well as imaginary numbers. It is denoted by script C, and it contains elements of type a plus bi, where a and b are any real numbers, and I is square root minus 1. Next we will discuss about types of sets. There are several type of sets. First one is empty sets. A set which does not contain any element, it's called empty set. It is also called as null set or void sets, and it is denoted by Greek alphabet phi. Next one is finite set. A set which is empty or consists of finite number of elements. For example, set A is equal to 2, 3, 5, 7, 9, or this is n4. It is a set of all first 4 natural numbers, 1, 2, 3, 4. So these both are finite sets. It contains finite number of elements. Next one is infinite set. A set which contains an infinitely many elements. For example, all listed above sets: set of natural numbers, set of integers, set of whole numbers, set of rationals, reals, complex. These all are examples of infinite sets. Then one important definition, that is cardinality of a set. The cardinality of a set is a measure of a set size, meaning the number of elements in the set. And that cardinality of any set is denoted by mod A, but we can read it is cardinality of A. For example, if A has these elements 2, 3, 5, 7, 9, then it has exactly 5 elements, so cardinality of set A is 5. Similarly, n4 has exactly 4 natural numbers, first 4 natural numbers, so its cardinality is 4. Then cardinality of empty set. Empty set contains no element, so its cardinality will be 0. Set of natural numbers is basically infinite set, but it is countable. So it is notation that we can denote cardinality of n is aleph null or aleph naught. Similarly, cardinality of real numbers or cardinality of complex numbers, they are uncountable sets, so it is cardinality of such a uncountable sets is denoted by aleph 1 or sometimes C. Then next concept we will discuss, that is subsets. A subset is defined as a set A is said to be a subset of another set B if every element of A is also an element of B, and in mathematical notation we denote it is A contains in B, or sometimes A contains or equal to B. In other words, A contains A is a subset of B if whenever A belongs to A, that small element A also belongs to that set B. For example, in above listed examples, set of natural numbers is a subset of whole numbers, which is subset of set of integers, which is again subset of set of rational numbers, and this rational number is a subset of set of real numbers, and then it is a subset of complex numbers. Next concept is power set. Power set is defined as the collection of all subsets of a set A is called the power set of A, and it is denoted by P of A. Basically, in P of A, every element is a different set. For example, if A is equal to 1 comma 2, then its corresponding power set will contains exactly 4 elements, and these are empty. Empty set is always a subset of A. Then singleton 1, singleton 2, and set A itself. Similarly, if we consider another example, capital B is equal to A comma B comma C, then its power set contains exactly 8 elements, that is empty set, singleton A, singleton B, singleton C, then subset A comma B, A comma C, B comma C, and lastly set B itself. Then we can observe one important remark here. If elements cardinality of set A is n, then cardinality of its power set is exactly 2 raised to n. Then there are some standard operations on sets. First one is union of sets. So if A and B are any two sets, then their union is defined as X such that X belongs to A or X belongs to B. For example, if A is equal to 1 comma 2 comma 3, B is equal to 3 comma 4 comma 5, then A union B is given by 1 comma 2 comma 3 comma 4 comma 5. That's mean union contains all common elements which belongs to either A or belongs to B. Another important operation is intersection of sets, so which is defined as A intersection B is equal to X such that X belongs to A as well as X belongs to B. So for example, if A is equal to 1 2 3, B is equal to 3 4 5, then their intersection contains only one common element, that is 3. Then next operation is difference of sets. So if A and B are any two sets, then its difference is defined as A minus B is equal to X belongs to A such that X does not belongs to B. For example, if A is equal to 1 2 3, B is equal to 3 4 5, then its difference also denoted by A slash B, and which is exactly 1 comma 2. Another very important concept, that is complement of a set. If X be a universal set for some particular example, then complement of A is defined as A complement, or sometimes we can write A dash is equal to U minus A, where U is equal to 1 comma 2 comma 3 comma 4 comma 5, and if you take A is equal to 2 comma 4, then A complement is equal to U minus A, and which is exactly 1 comma 3 comma 5. Another important operation, which is symmetric difference, it is denoted by A symmetric difference B, and which is defined as A difference B union B difference A. For example, if A is equal to 1 comma 2 comma 3, B is equal to 3 comma 4 comma 5, then A symmetric difference B is equal to 1 comma 2 comma 4 comma 5. So symmetric difference contains elements which belongs to either A or B, but not in both. Then we define Cartesian product of a sets. Given two non-empty sets A and B, then their Cartesian product is defined by A cross B is equal to It contains order pair of type A comma B, where A belongs to A and B belongs to B. For example, if A is equal to A comma B comma C and B is equal to 1 comma 2 comma 3, then its Cartesian product contains exactly 9 elements, and which are A comma 1, A comma 2, A comma 3, then B comma 1, B comma 2, B comma 3, and lastly C comma 1, C comma 2, C comma 3. All possible order pairs between A and B